In this talk, Rick's going to show us how GPU computing is done in order to speed up the network's graph. And the next voice you'll hear is Rick.
Thanks. Good morning. So today, obviously, I'm going to talk about GPU accelerated NetworkX. I'm guessing by the title that most people are probably familiar with the library, but maybe just a quick show of hands who has used NetworkX. Okay, good. Because I don't really talk too much about the background or history of NetworkX or why it's so easy and use, I'm going to talk specifically about GPU acceleration for it. So what is GPU accelerated NetworkX? I'm going to cover that and some of the background and how we got there. And then who it's for. It's probably not for everyone because it's kind of more custom tailored for larger graphs, which is something that NetworkX doesn't do very well. I'll talk a little bit about how this changes things. It's not simply about just going faster. It sort of unlocks more options for NetworkX and all the users that use that very popular library. I'm also going to cover how this works, not just internally, how the mechanism works to GPU accelerate NetworkX, but also how you can use it. And then finally, I'll sort of go over a brief roadmap or options, and maybe open it up to requests and things, because we're all this, it's an open source project, so we're always looking for new ideas. So yeah, what is GPU accelerated NetworkX? I want to emphasize that it's NetworkX, but with key algorithms accelerated using NVIDIA cugraph, which is part of the Graphics project. It's not a separate fork of NetworkX that we changed to do GPU calls, or it's not even a separate library that was kind of NetworkX inspired. We did try that, and I will talk about that a little bit. But this is actually NetworkX, the same NetworkX you install when you do install NetworkX. That's the foundation of the whole thing. And the GPU acceleration is made possible through NetworkX support for third-party backends. This was added in NetworkX 3.0. The current version right now is 3.4.2. So since 3.0, we've added various features that we've taken advantage of to accelerate NetworkX. And obviously the result here is the same NetworkX code you have written or someone else has written, only faster than the GPU is present. You might hear us call this zero-code change acceleration. There's other techniques too, but the emphasis here is that you don't have to do anything. You just install the software with the GPU and then run your code like you did before. In fact, on the right here is these little code snippet at the very top. You can actually type that in. It's just 6 lines. And then I use IPython to use the time magic, but you can see without acceleration on my workstation, it took almost 8 minutes, and then with it took about 5 seconds. So the exact same code, get the same results. So it's pretty neat that you can use this familiar library that you all run accustomed to, and just have it go faster. I mentioned Rapids before, so let me give you a little bit of background on that, how we got here. So Rapids is a project at NVIDIA. It's a suite of PyData libraries, popular ones used by data scientists. We have a data frame library, machine learning library, graph, of course, and others. And the goal, of course, is to bring GPU acceleration to the PyData ecosystem users. So if you think about, years and years ago, data scientists wrote C and C++ and Fortran. They wrote these libraries. High-level languages like Python came along. Has anyone used? I remember I wrote a lot of Sickle code to a command language. High-level language that wraps these performance C++ or C libraries. And that was nice because it unlocked the ability to just kind of interactively use my library. I didn't have to recompile main.c every time I wanted to change a little thing and run a out. So that was great. And then people discovered these graphics processors are great for compute as well. But it's a whole separate device. It's not just a matter of porting from x86 to ARM, but a completely different paradigm. CUDA came along, which meant C and C++ users, which are familiar with that, can access these paradigms and kind of reduce the barrier to entry for using GPUs. So naturally they started writing libraries, CUDA, C, C++. And you can see where this is going. So we want the ability to use these high-level languages too for the GPU accelerated libraries. And that's what Rapids is. So Rapids lives in that space, and it's a suite of libraries. If you know pandas, you can use cuDF. If you know scikit-learn, you can use cuML. If you know NetworkX, you can use cuGraph, scikit-image, cuSIM, there's others. But you can see there's an issue here already. So on the left there is your typical pandas NetworkX code. And on the right in green is the Rapids equivalent. So you import cuDF and import cuGraph. And you can see that it's very similar, but it's not quite the same. I still have two different stacks here that I'm working with. And you can imagine, like, you can write some code to abstract that away. And if GPU is present, call this, and if not, call that. Not too hard. But in the end, it's still a burden. And it only runs on GPU, so you have to have GPU there to even import it sometimes. So the solution here is to just take that abstraction that I referred to, mentioned, add it to the top to make both of those stacks available, essentially. So now I can just focus on the quote-unquote standard way of doing it as a NetworkX. And so this NetworkX backend that we have allows us to do that. There's also pandas. It's not really a backend, but it's the same idea, zero-code change equivalent for pandas, called pdf.pandas. And I can enable both of them and run this script without changing and get GPU acceleration. Yeah, it's almost equivalent performance-wise to the native using just the Rapids libraries. And so the different libraries enable them in different ways. So the nx-cugraph for NetworkX uses an environment variable. The PDF pandas uses a module that you can execute anything like that. But the end result's the same, just faster versions of your code. So stepping back, what is cuGraph again? That project consists of a whole stack of different libraries. And as a user, you can use any of them. You can use the C++ one for your C++ project. You can use a low-level Python one that we use, that we've built our higher-level libraries on top of. So we have the cuGraph one that I showed you in the green box before. We have the NetworkX backend, nx-cugraph here. We also have libraries for GNN extensions for DGL and PyG. So that's cuGraph in a nutshell. Now, going back to NetworkX and accelerating that, who is this project for? Well, like I sort of alluded to earlier, it's for NetworkX users that have been kind of frustrated that, when their data reaches a certain size, the performance starts going down. They want to continue using their code on larger data. With this solution, they just add a GPU, enable the environment variable, and then there. So you can sort of see this is a very rough, hand-wavy trend of performance over graph size. The green line, of course, is the accelerated version of NetworkX. And then without it, you start to see performance degrade as the size grows. So we've sort of roughly characterized large here as about 100,000 nodes and million edges. That's where a lot of the NetworkX algorithms start to really struggle. But again, if the data is small enough, NetworkX without acceleration is pretty good. Works well. So these are some benchmark plots that we did. You can sort of see there's a variety of different data sets that we used there. And they're ranging from the very small, 1,000 nodes, 5,000 edges, to larger, 5 million nodes, 69 million edges. And you can sort of see that trend, like I mentioned. There's that point where NetworkX, for a lot of the algorithms, performance starts to degrade. It's usually in that middle, in this case, 264 nodes and million edges. So, the time along the y-axis there is in seconds. Some of these algorithms, for when data gets that large, you're talking, like, for between a centrality there, that's 7,000 seconds. That's almost a 2-hour run. cuGraph, accelerated NetworkX, beats that in 10 seconds, which is good. So the GPU is great for a lot of these problems because of the parallelism. You can see, well, if I could zoom in on this plot, you can see the run times for a lot of these as the graph size increases doesn't really change because the GPU hasn't even gotten saturated yet. It's only until it gets to the much bigger size that you start to see the 5 seconds, 10 seconds. But not all of them are optimized yet. We have roughly 60 algorithms supported. Here's some that don't perform quite as well. We're still working on those. shortest paths in DFS. So they perform about as well as NetworkX up until a certain point. And they do speed it up some, but not the 100x that you're seeing for some of the others. But this is part of our roadmap too, that we'll continue optimizing these. Part of our challenge is that NetworkX being so flexible, the return types are so dynamic that we have to convert a lot of the GPU-based data structures, convert those to Python lists and Python dictionaries on the host. So that kind of overhead sometimes eats into our performance, but we're improving that. So how does this change things? It's not, like I sort of said earlier, it's not just a matter of going faster, but now I can write portable code, I'll call it. So I can write that same NetworkX script and run it on my laptop, and then I can take it to production with much bigger data on a workstation that has a GPU and run that same workflow there. I no longer have to think about, well, NetworkX was great for experimenting with this graph problem, but now I have to rewrite it with iGraph or something else when I go to production. I can use the same code and use all the same documentation and examples. So I stay in NetworkX, I get that kind of zero code change experience. And then, but most importantly, when I'm using NetworkX for exploring these graph problems, I can start thinking differently now. I no longer have to worry about runtime considerations or this data is too big, so I really can't look into it as much because it's just going to take too long. Start the run and go home and then come back in the morning and see where it's at. I can just start it now, see where it's at, and try 10 more different things if I want. So case in point here, between the centrality, that's one of the algorithms I mentioned earlier. I found a data set that had ground truth values for the results of the centrality. So I use those, which is a third-party verification of both NetworkX and cugraph, which is nice. But you can see on the left of each of these tables is the actual top 5 values of between the centrality scores for the nodes in the graph. The K refers to the number of samples that it takes. Between the centrality is an approximation algorithm that uses, uses samples in the graph, computes shortest paths between those samples, and then determines how many times each node falls in the various shortest paths. And so if it falls in that shortest path a lot, then it's an important connected node that's central to various parts of the graph. So you can't really, for the graph to get large enough, NetworkX can't sample every single one. So they have this K value to say, okay, well, you can get an approximation if you've done it on K, you can get it done in a reasonable amount of time. So you have to take K into account when you're using NetworkX, much more so than an accelerated version. So you can see here, K equals 1, 10, 100, 1,000, 10,000, and then none, which is all the samples. If I want to get the actual deterministic values, I have to use all the samples. And if I want to use NetworkX on this data, it's going to take me over half an hour. If I use accelerated NetworkX, it's 3 minutes. 3-minute equivalent is about 1,000, K equals 1,000. And you can see I'm not sort of sacrificing some accuracy here. So again, this is well, now I don't have to sacrifice anything. I can just use the GPU, always get deterministic results between centrality. So it's kind of, like I said, it changes how you think about the problem now. Another one I thought about was this recommendation system. So if you have a bipartite graph like this, you can do this projection, and in this case, the red numbered nodes are movies. The blue lettered nodes are reviewers. If I project down into a graph of just movies, I can use those edges that represent the reviews of the users on those movies and get a relationship between the movies of similarity. The weights account for how similar they are. And so this is a technique that you can use for a recommender system like this. They've also used it for fraud detection, finding anomalies like that, similarities between transactions and that. So if I use a personalization vector with PageRank, I can get basically these recommendations. So this personalization vector represents what a user prefers. And so it sort of pre-weights the graph for that user and introduces bias. So without the personalization vector for this little example here, you can see node 4 is the highest page ranked node. I have this personalization vector that says this person really prefers node 3. Now node 1 is the highest. Node 3 is higher than it was before. But you can see because page rank, node 1 is referred to by node 3, so that ups its popularity. So this is how this roughly works. Now if you take a data set like the movie lens one, which I'll talk about in a second. But anyway, this is the code. This is, I guess, the key part of the code here. Just simple NetworkX page rank calls. So that's the great thing about it. Again, I can use it on this toy example, but then I just throw the real data at it, and it continues to work. In the case of the real data here, I used a data set from this site called Movie Lens. And in this case, I've got 330,000 users and almost 34 million reviews with an average of about 100 reviews per user. So it's a lot of data. The projected graph here, movie graph, the red one in the previous slide, is 875 million edges. So it's giant. But you can see, and it's not going to be a replacement for like edge prediction in a graph neural network that would probably do a lot better for recommendation, but it does sort of get you there. You can see how the bias comes into play. So in this particular case, this user saw these top 5 movies that they liked, and it recommended The Matrix and Star Wars, which maybe they're close, I don't know. I made another hypothetical user that likes all these romance movies, and you can see it did change the results. So maybe there's something there. But the point is that this is maybe represents a real world problem, and I'm getting some results that are looking close to what I'm expecting, and I would want to do a lot of tuning, which would mean a lot of kind of interactive runs and experimentation. Now I'm going to use NetworkX for that as is with this data. That first page rank call took about 2 hours. The second one took about an hour or so. If I turn on the GPU and just set that environment variable, I get that time in less than 2 seconds for both of those. So you can see again how this changes how you work. Now I can try lots of things, and I can keep experimenting. And I'm using the exact same data and the exact same code. But, a lot of critique we get for this approach is, why are we comparing performance to NetworkX? Aren't all libraries faster than NetworkX? NetworkX's strength is its usability, its documentation, its community. Everyone knows it. If you ask ChatGPT, how do I find the between the centrality values for each node in a graph? I didn't say anything about Python. I didn't say anything about NetworkX. And it says, step 1, install NetworkX. So everyone's using it, and everyone has known it. So it's like, it makes perfect sense to say, all these people that are using it, that want to keep using it, they shouldn't have to abandon it when their data gets stupid and go to a different library. Now they can just access the GPU either in Colab or different cloud service providers or locally, and then keep going as their data gets larger. So that's kind of why we compare against NetworkX. It's really, 100x speed up from what you're doing before, not necessarily against other libraries, because there are other libraries that are optimized for different CPUs that are going to go pretty fast and quite performant. But it doesn't really matter if I have to abandon my whole work change it. Some people do that, but that's like not the audience we're talking to. And again, like I said, probably the most popular library, not just in Python, but indeed in any language. Roughly $80 million as of last month. So popularity matters, obviously. It's going to be bigger, going to be more documentation. ChatGPT knows the answers for it, so why not allow ChatGPT to go faster too? So how does this all work? I mentioned NetworkX adding support in 3.0 earlier for these third-party backends. This is referred to as function dispatching. It happens at runtime, and you can sort of get a rough idea of the flow here, where NetworkX finds the installed backends. You call a function. It checks, do any of the backends out here support this function? And if so, it'll call the first one in the prioritized list that you gave it. So you can use multiple backends even. So there's a graph database backend that allows you to store data in a graph database, and then combine that with the GPU backend, and then you can run accelerated algorithms on the GPU. There's other backends for CPU, graph loss, nx-parallel, those parallel versions of NetworkX. You can combine all these, and each backend doesn't have to implement the full, 200-ish functions that NetworkX supports. cugraph, for instance, only supports 60-ish or so. So the NetworkX dispatching mechanism will understand that, and it will fall back to regular NetworkX default implementation if the backend isn't supported. So again, this is all seamless, zero code change. But there are other ways to call it too, which I'll talk about here in a second. You're probably wondering too about that NetworkX graph implementation is, if you're familiar, is a dictionary of dictionaries implementation. So it's all Python, super flexible, one of the strengths of it, but not always very performant. And then cugraph is going to require a completely different implementation of that graph on the GPU in like CSR format or COO format or some other optimized matrix type representation. So that's a conversion that happens internally. And NetworkX manages all those too. That'll happen automatically if it's been converted before. It'll maintain cache if you've enabled that. So the conversion hit doesn't have to happen every time. If you change the graph, because NetworkX is a full dynamic heterogeneous graph type, it will automatically take care of the value of the cache accordingly. It'll all just work. So that's nice. You can get an idea too of another way to, I'm sorry, I'm going to end this up here. But this is roughly how you would use it. One key point too is that environment variable nx-cugraph autoconfig. This is a shortcut that cugraph implements. What it really does is internally it expands to about 3 configuration options that if you're using other backends, they give you kind of a fine-grained control about I don't want to use caching, or I do, or I don't want to dispatch to graph generators, or I do, and so on and so forth. In most cases, they just want all those things on. So cugraph gives you nx-cugraph autoconfig true, just turns everything on for you. And you can combine that with the other options, which you can read about in NetworkX docs. That should all work too. Like I mentioned earlier, the zero code change approach is probably the most popular kind of dispatching technique, but there are others. And they come in really handy for different situations. Like here you can see I can use this explicit dispatch. You might informally call that a low code change option. Each one of the NetworkX functions that supports dispatching will add a backend keyword argument where you can just explicitly specify what backend you want to run. So obviously this code here is portable to systems that don't have a cugraph backend, but it does allow me to say, like, I don't want you to do that failover thing. I just want to fail if it's not there. I don't want to know what's going on there. So you can just dial that in right there like that. Another way to do it is the kind of using type-based dispatching. I mentioned earlier that different backends may have different graph representations. Well, in your code, you can actually instantiate those directly in some cases. So for cugraph, I can just make a cugraph object right off the bat. And that's going to, every time I add data to it, the GPU is going to get updated. There's no internal conversion happening. So when I call PageRank in this case with that explicit graph instance from cugraph, it's going to just use the cugraph backend. I believe in 3.4.2, it will also convert it back to NetworkX if the backend, if I call the NetworkX function, which is not supported by cugraph. So it tries its best to keep everything working as much as you want. Again, you can present that via various configuration options or just saying backend. Yeah. And then lastly, the graph creation functions. Those are also dispatched and return back in graph types. So this is a new feature in NetworkX 3.4. And this gave us a big speed up too, because if you see, it's a pretty common pattern, especially for bigger graphs, to be loaded by a file on disk, like a CSV, for instance. You read that in with pandas, get a data frame, and then create your graph from that data frame. Prior versions would say, with this code, well, we need to return a NetworkX graph type because we don't know what's going to happen with this. It might be like return a backend graph type and call a NetworkX function that's not supported by that backend. That would be a problem because they didn't have the failover in place like it is today. But now we can return a backend graph type based on that priority. So if you say cugraph is the backend I want to use first, it's going to return a cugraph graph object. So that data frame will get loaded right onto the GPU, and then every algorithm that you call that cugraph supports will not have to be converted. So those big speed ups that you saw in the prior examples took advantage of all these features. And then last, but probably very important, not least, is we've also included debugging mode in NetworkX itself. So it's just using standard Python logging APIs. If you enable debug logging and then run those examples, you can see all the decisions that are being made behind the scenes. And if you're ever wondering if, is it using this backend or what's going on here, you can turn on debugging and get that information. So where do we go from here? Well, like I showed you in that slide, not all of our algorithms are getting the tremendous speed up that we want. There's a lot of overhead, like I mentioned, and just various conversions that go from, converting the optimized GPU representations to the flexible Python ones. So we want to improve on that. The cugraph Python library, not the NetworkX one, I want to show you earlier. That one supports multi-GPU, multi-node distributed using Dask. We have a lot of clients that use that Python library to get gigantic graphs processed. We could bring that to NetworkX too if there was a demand. So this is all part of our roadmap prioritization. So always taking feedback. And then one of the most popular uses of NetworkX is plotting. Obviously, used quite a bit for the smaller graphs. As the graphs get larger, they just turn into hairballs, I guess. But even so, is plotting something that would be interesting here too? There's separate projects at NVIDIA for plotting graphs. Might be interesting to bring those into the NetworkX ecosystem too, and have NetworkX users take advantage of that seamlessly. But in general, we're looking for all sorts of feedback about use cases in the community. The algorithms I showed earlier, PageRank, between the centrality and the domain, those are all popular ones that we actually have requests for. So we prioritize those highest, but further requests will help us prioritize even further. So feel free to file an issue. We have the nx-cugraph repo and then the cugraph repo as well for the other parts of that stack I showed you. There's a intro notebook on Colab. Colab has support for GPUs, and you just enable that, so you can try it right for yourself. There's a small graph example and a larger graph example. And in general, there's just more information here at this landing page there. With that, we'll take the questions.
Thank you so much, Rick, for your time. So we'll have Q&A. Yeah.
You mentioned some implementation details that slow down certain algorithms, but are there algorithmic limitations for parallelization?
I think there are. I think there's some algorithms that are more parallelizable, more suited for GPU than others. I'm probably not the best person to answer that one. The cugraph library, the C++ one, has some algorithms we haven't exposed into NetworkX yet, so we're doing that. But and like I said, some perform better than others, even in C++. But I think the short answer is yes. But I don't know which ones are. I can find out.
How different are the representations of the graph between normal NetworkX and cugraph?
They're pretty different. So NetworkX's representation is a pure Python dictionary of dictionary of dictionary. So it's a dictionary consisting of nodes as keys and a dictionary of edges, and each edge is itself has attributes on it, and each node can have attributes on it. So dictionaries all the way down. Cugraph is a homogeneous graph type. It's not a proper graph like NetworkX. So it's just numerical, zero-based nodes and edges for that. You can have a weight value too.
So no labels like strings or whatnot?
That's right.
Why can't we just have like a string of, let's say, 8 characters, and that's just a 64-bit integer?
Yeah, so in the nx-cugraph layer, the mapping, the backend part, all that stuff gets mapped into basically values like that for the weight, for instance.
Okay, so with no labels.
Right.
Okay.
Yeah, the labels would get mapped in that conversion layer, kind of hence some of the conversion overhead we have.
So you do allow labels, it just gets mapped.
Right.
Okay,
right.
cool.
So all the NetworkX attributes that you put on a graph, you can continue using those.
You used a bunch of different, you showed benchmarks, and you used different GPUs for those benchmarks.
Yeah.
Are there any guidelines on the hardware for different types of algorithms or any hardware issues that we need to be aware of?
Right. So the different algorithms probably perform, in other words, there's not a GPU that's optimized for a particular algorithm. Typically, we just go bigger GPUs like this giant recommendation. This is 800 million edge graph. I had to find a 80 gigabyte GPU for that, which just happens to be an H100, which is pretty fast. So, if you go to Colab, for instance, I think the paid tier, they have A100 80 gigabytes, which would probably be a little slower than this, but not like 2 hours still. And then a lot of the benchmarks, and we have other benchmarks available that use like a T4, more commonly available one too. I don't have those numbers on. They're a little slower, not drastically enough. But in short, there's no recommendation for this particular GPU for this particular algorithm. It's usually just bound by the graph size, how you pick it, scalable. Oh.
Is it more memory bandwidth, or more like some of the algorithms aren't exactly parallelizable, so you have to do more compute? But I'd imagine it's more memory bandwidth now.
Yeah, we run into memory limitations first, for sure.
Without the memory size limitation, I mean.
Oh, without the memory size? Yeah. I couldn't tell you because it's probably more compute than at that point.
Have you considered like compressed graphs? And I don't just mean like CSR or whatever like the thing is. I saw this paper about like LZW compression for like graphs.
Oh, okay. Yeah. Yeah. For that one, we're kind of limited. This project is kind of limited by what our C++ team gives us. We just convert to the representation. I don't know if they're using if they have that on their roadmap for supporting that format or not. And I also know for like the larger multi-GPU cases, which this does not support, they'll go DCSR, for instance, for other things, or super sparse type matrices, distribute those.
Speaking about sparse matrices, matrices? Do you guys use like graph loss?
We don't, but NetworkX has a graph loss backend.
Okay, cool, awesome, yeah. Because then the GPUs with sparse matrix optimizations, because it's like that would 2x stuff.
And I know the Graph Plus project, other members of the cugraph team are working with those guys to GPU accelerate Graph Plus too.
There was like a Neo4j talk yesterday. Does NetworkX have anything to do with like graph stuff like Neo4j?
You mean like a graph database support?
Yeah.
The cugraph project doesn't do graph database attributes. I think the closest thing we had was we did an experimental property graph type, but there was no like query aspects to it. It was just, you could use it in a rough, thinking of it like a database. Like
Rough approximation.
Yeah,
but database.
we usually rely on other companies to GPU accelerate them. Graph. Yeah.
So is there any kind of like a validation metric or anything in order to check how the network is working?
So we test the various, well actually if you go to the intro notebook here, I try to evaluate, for PageRank, for instance, I compare all the values and the numerical tolerance, and then between the centrality, we do exercise, since that's an approximation algorithm, I'll look at these values. And for instance, when I'm getting deterministic results with all the samples I verify that they're all equal. But it varies on algorithm. We try to basically use NetworkX. NetworkX is the reference implementation compared to those.
So that 3 minutes and that 8 minutes, it's on what basis? How much data?
So that graph was 33,000 nodes, 180,000 edges.
Okay.
And that's like relatively small. But even still, if I wanted to use all the samples, 8 was 9, that took 3 minutes on GPU. If the graph gets bigger, it's still not feasible to say K. That's why K exists as an option. Yes.
What about build graphs and dependency graphs? Like they're a bit more sparse, or like tree-like sometimes, or like list-like sometimes. But have you seen that use case?
I think NetworkX sees that use case.
Okay. Nice.
Like dependency graphs and build graphs. Those typically, it's going to be hard for those to reach the 800 million edge case probably.
So I used to work at Twitter where I was doing build graph stuff, and I was like, what if I just, it wasn't 800 or 8 million or whatever, but the stuff that we had to do on it was like a lot.
I see.
To, if we wanted to like be efficient in other phases of build, then we could do more in the graph analysis part.
Right, yeah. That would have been a good case to try
Nice.
on because
We can still try on like open source stuff. Like
yeah. Oh, that's another point I forgot to make. With the zero code chain approach, projects that use NetworkX in a way that for the users of those projects, they don't necessarily have access to how NetworkX is being called. With the zero code change acceleration, those projects will see potential speed up too because they don't have to change anything.
And how many edges, for the zero code change, how many edges is typically like a pretty good size for both like a minimum for like to overcome the overhead and also the maximum in terms of like if I don't want a 8100, let's say I want like 16 to 40 gigs of VRAM.
Yeah, see that was hard to kind of quantify because it varies on the algorithm, the overhead and stuff.
But like say a million edges, is that going to be okay?
That's kind of, we roughly said, 100,000 nodes, a million edges.
Okay, cool, awesome.
Yeah. And then the graph, we had that middle graph here, Amazon 0302. That one was 260,000 edges, 20 million nodes. And that was typically when a lot of these benchmarks you see it starting to break away. So that's kind of where we got that.
Is there a difference between like algorithms for trees and DAGs versus general graphs that like could have anything?
Yeah.
In terms of like performance or not
Right.
but performance.
I think, and that's a good point too, because the graph type itself can influence performance. like you can see in this Louvain benchmark, for the Hollywood graph, it spikes way down because for Louvain, this one has, Hollywood has fewer nodes, but a lot of edges. And so that gave Louvain for NetworkX better performance than if it had a lot of nodes. So,
Okay, so a little bit more.
So sorry, we need to stop right now because the next session will
Okay.
start in 5 minutes. He's going to take the questions outside.
The talk was just too good.
I agree.